Good morning. So in today's class we look at two more basic results. So that's axiom of choice and infinite direct products. Now let us start the axiom of choice. So axiom of choice is one of the important axioms in set theory. The simpler meaning of axiom of choice is, so if you are given a collection of sets, so from each collection I can choose a representative element. Say for example, if an election is happening in the college, okay, so we will form a parliament in that case. So the members are elected to the parliament from each class. So given a class, you are finding a representative from each class. So there you have a representative corresponding to each collection, where your collections are different classes. അപ്പോൾ നമ്മുടെ ക്ലാസ്സസ് എന്ന് പറയുന്നത് കളക്ഷൻ ഓഫ് സെറ്റ്സ് ആണ്. അപ്പോൾ ഓരോ ക്ലാസ്സിലും ഞാനൊരു പെർട്ടിക്കുലർ മെമ്പറിനെ എലക്ട് ചെയ്യുമ്പോൾ ഐ എം ഗെറ്റിംഗ് a representative for that particular class അല്ലെങ്കിൽ particular set. So such a choice making is always possible. അതായത് given a collection, it is always possible to represent it by a single element. So this principle is the simpler meaning of axiom of choice. So let us state axiom of choice. So let script C be any collection of non-empty sets then there is a function f defined on script C which assigns to each set A belongs to script C, an element f of A in A. So we have script C to be a collection of any non-empty sets. Then by axiom of choice there exists a function f defined on script C. So it assigns to each set A an element f of A. So corresponding to every element A in the collection, we are assigning an element in the set A. So the function f, we call it as the choice function. So function f is called the choice function. Axiom of choice. So if you look at the collection C, so that's a collection of non-empty sets. This collection can be either finite or either that can be also infinite. So the axiom of choice is valid when you have a finite collection or infinite collection of sets. Now let us look at what do we mean by a direct product. So let us consider two sets, say x1 and x2. So you know what is Cartesian product. So by the product x1 x2 we mean, so here x1 and x2 both must be not equal to 5. So this is the collection of all ordered pair of elements such that the first element belongs to the set capital X1 and the second element belongs to the set capital X2. So each of the sets x1 and x2 must be non-empty. Now this can be extended to any number of indices. So that product is called as the direct product. Okay. Let us now define the direct product. So let C equal to x lambda be a collection of sets indexed by index set. So this lambda belongs to the index set capital lambda. Then we define the direct product. So that will be product over lambda x lambda. Figure what denotes the product sign. So that is product over lambda x lambda to be a collection of all sets x lambda indexed by capital lambda and having the property that so small x lambda will belong to capital X lambda. So we define the product, direct product of capital X lambda to be so the ordered pair പറഞ്ഞ പോലെ so here we will be getting a set which is indexed by index at lambda. അപ്പോൾ capital lambda elements ഉള്ള ഒരു സെറ്റ് ആയിരിക്കും അതിൻ്റെ ഒരു പെയർ പോലത്തെ ഒരു സാധനമായിരിക്കും കിട്ടുക such that each element small x lambda belongs to capital X lambda. So the first element will belong to capital X1, second element will belong to capital X2. So that is the definition of the direct product. So put in this form, so if z equal to x lambda is an element of direct product of lambda x lambda, then we call x lambda the lambda coordinate of z. So the lambda coordinate of z will be small x lambda and that belongs to the set capital X lambda. When you take a direct product, the x lambdas must be non-empty, and if one of the x lambdas is empty, then the entire product becomes empty in that case. So if one of capital X lambda is empty, then in that case the direct product X lambda is also empty. The axiom of choice can also be stated using direct products. So let us look at the axiom of choice. For other, each statement in the converse statement ആയിരിക്കും വരുന്നത്. So here we have seen the statement that if one of the x lambda is empty, then the direct product is also empty. So the converse statement is if none of the x lambda are empty, then the direct product is not empty. So if you have a collection of sets, then corresponding to that collection നമുക്ക് ഓരോ സെറ്റിനും കറസ്പോണ്ടിങ് ആയിട്ട് നമുക്ക് ഓരോ കോർഡിനേറ്റ് കിട്ടും. ഫസ്റ്റ് സെറ്റിന് കറസ്പോണ്ടിങ് ആയിട്ട് നമുക്ക് ഒരു x1 കിട്ടും, സെക്കൻഡ് സെറ്റിന് കറസ്പോണ്ടിങ് ആയിട്ട് നമുക്ക് ഒരു x2 കിട്ടും. So on corresponding to the lambda set, you are getting x lambda. So corresponding to each set, you are actually getting a representative element. So the converse of this becomes the axiom of choice. So let us state the axiom of choice also. So the axiom of choice is equivalent to the converse statement. So that is if none of the x lambda are empty, then the direct product of lambda x lambda is empty. So if none of the sets in a collection are empty, so corresponding to each set we'll be getting a representative element. So this is another version of the axiom of choice. Let us look at a few more results on open and closed sets of real numbers. So we will just look at the results. So the simplest sets in the real number system, they are the intervals. And when you take the real life, so you can have intervals. So these are open intervals, so that is a less than x less than b, and then we have closed interval a b, so it includes a and b, so that is of the form a less than or equal to x less than or equal to b. Then you have semi-open intervals. So here you have a is not included, but b is included in this case, and then you can have closed a, open b. And we can also have infinite intervals. So infinite intervals, so that is either of the form a to infinity and b minus infinity to b, or we can have the entire real line, so that is minus infinity to infinity. So these are the different intervals on the real line. So let us now define what is an open set, and let us see a few results which you have already learned in the previous courses. So let us give a definition of open set. So a set O of real numbers is called open. If for each x belongs to O, there is a delta greater than 0 such that each y with mod x minus y less than delta belongs to O. Suppose open if for x in O, there is an open interval I such that x belongs to I, which is contained in O. That means every point in the set must be an integral point. So corresponding to every x, there must be an open interval I, which is again contained in O. And as you know, all the open sets are all the open intervals in the open sets. So open intervals are open sets. Then phi and r means the empty set given set of real numbers is open. So these are the open sets. So these are sets which are always open. A few more results. Section 2 open sets and 2 will be again open. Then the intersection of any finite collection of open sets is open. So finite intersection of open sets is again open, and the union of any collection of open sets is again open. That is arbitrary. Union of open sets is open. So these are some of the results related to open sets.